Part 2 of Lesson 5, we'll be covering thermal equilibrium and talking about heat and phase changes and doing some calculations. Looking at thermal equilibrium or heat equilibrium. So for thermal equilibrium, this is when we have a hot substance and a cold substance, so two substances at different temperatures, and we bring them close together in contact with one another. So whether these are solid blocks like in the diagrams or liquids that we're pouring into each other. So once we put the hot and cold objects or substances together, what's going to happen is heat is going to be transferred. Now heat is always transferred from the hotter object to the cooler object, and heat continues to be transferred until we reach an equilibrium, meaning that both substances become the same temperature. So that means that the transfer is complete once both substances equilibrate and reach the same temp. So in the diagram or the example shown off to the right, we have a wood block and an aluminum block. The wood block is at a temperature of 25 degrees Celsius, the aluminum at 75. So when we bring them into contact with each other, what's going to happen is that aluminum block, which is hotter, it's going to transfer its heat to the wooden block, making the wooden block become warmer. But since it's transferring its heat, as it makes the wooden block temperature go up, the aluminum block temperature is going to go down. And this process is going to continue to happen until both objects reach the same temperature. In this case, they equilibrate at a temperature of 41.9 degrees Celsius. So looking at how this is transformed into an equation, we have an equation here where heat lost, that's what this Q lost means, heat lost plus the heat gained is equal to 0, because heat is a form of energy, and we said that energy cannot be created or destroyed. That was the first law of thermodynamics. So if heat cannot be created or destroyed, that means the heat lost is going to equal the negative value of the heat gained. So the heat lost is always going to be the hotter object, because the hotter object is the one losing the heat. The heat gained is going to be the cooler object. That is the one that is gaining heat from the hotter object. So we can set these equal to each other, but their values are opposite. So the heat lost is generally a negative value, and the heat gained will be the same amount, but the opposite sign. So one positive, one negative, but the numerical values are the same. In the case of the aluminum and the wood then, since the aluminum was the hotter object, that's the object that is losing heat. So it's going to have a negative Q value. And the wood, since it was gaining heat, will have a positive Q value. So let's look at an example of conservation of heat. Here we have a hot iron bar being plunged into water. So the hot iron bar is the system. As you can see in the diagram off to the right, it's going to be this lighter lavender colored square inside of the water. So the system being that hot iron. The water then, of course, being the surroundings. So since energy cannot be created or destroyed, the heat of the water, the heat of the iron plus the heat of the water are going to equal 0. So with this equation, if we move the iron to the opposite side of the equal sign, we get Q of water is equal to the negative Q of iron. So the reason that I moved iron to the opposite side, giving it the negative sign, is because iron was the hot object, so it's the object losing heat, giving it a negative value. Now, we know that Q, or the equation for heat, is mc delta T. So what we can do with this equation is we can take this mc delta T and we can plug it in to both the water side N2, the iron side. So when we do that, it becomes this extremely large equation. Okay, so we just took that MC delta T and we plugged it into both sides of the equation. One side representing the water side, and that's the positive side since that was the colder object of the two. The other side representing the iron, which is the negative side because that was the hotter of the two. Now notice we're putting subtitles on these, or subscripts on these, excuse me. So on the water side, we have mass of just the water, the specific heat of just the water, and then the change in temp of the water. Moving over to the iron side, same thing. Mass of just the iron, specific heat of just the iron, and then the change in temp. Now notice for the change in temps on both sides of this equation, we have the initial temp of the water on the left side and the initial temp of the iron on the right. But notice the final temp. The final temp we have no subscript by. The reason we don't have a subscript by it is because the final temp is going to be the same on both sides. Why is the final temp the same on both sides? Because that's the thermal equilibrium. That's the heat equilibrium that is reached. When we put a hot object with a cold object, heat is transferred from the hot object to the cold object, and this process continues until an equilibrium is reached. And when an equilibrium is reached, the temperature of both objects, the final temperature, is the same. So that T sub F on both sides of the equal sign is going to be the same value. All the other values will vary depending upon whether we're talking about the iron or the water. Let's look at a practice problem and how we're going to apply that modified equation. So in this problem, we have 44.7 grams of hot cobalt at an initial temperature of 132 degrees Celsius. We place that piece of hot cobalt into 124 grams of water, initially at 57.6 degrees Celsius. So we have hot cobalt going into colder water or cooler water. After a few minutes, the aluminum and water reach an equilibrium. So heat is transferred from the cobalt to the water until an equilibrium temperature of 60.2 degrees Celsius is reached. Now the question is asking us to solve for the specific heat capacity, so C, of the cobalt. And they give us the specific heat of the water. So let's start by writing a list of our knowns. So since we have two different substances, we want to make sure to label our variables indicating what substance that variable belongs to. So what I mean by that is, for instance, with the mass of the cobalt, we would just write M sub cobalt, indicating this is the mass of just the cobalt, 44.7 grams. We then have the initial temp of the cobalt, which was 132. Now moving to the water. The mass of the water was 124. The initial temperature of the water was 57.6. Now notice for final temperature, we don't label it as either water or cobalt because that final temperature applies to both the water and the cobalt. We also have the specific heat given to us of water. So what we're looking for then is the specific heat of the cobalt. So what do we want to do, or how do we approach this problem? Well, we can determine the heat of water, relate that to the heat of cobalt, and then rearrange the equation to solve for the specific heat capacity of cobalt. So the first step in our plan to approach this problem is determining the heat of the known substance. So in this case, that's going to be the heat of the water because they gave us the mass of the water, the specific heat of the water, and then also two temperature values in which we can figure out the change in temp of the water. So plugging those values into the equation, we have 124 grams for the mass. The specific heat was 4.184. The final temp, once the heat transfer was complete and it reached equilibrium was 60.2, and the initial temp of the water was 57.6. Notice this gives us a positive value of 1384.9 joules. Also notice that I did not round to significant figures yet because this is not our final answer. So keeping as many digits as possible will give you a more accurate answer. The next step is to relate that heat of the water to the heat of cobalt. So remember, we can set them equal to each other but with opposite signs. So whatever the Q value or the heat of water was, the heat of the cobalt is going to be the same value but opposite sign. So since the heat of water was positive 1384.9, the heat of cobalt is going to be negative 1384.9. From there, we can now solve for the specific heat capacity of cobalt. So we use the same equation, rearranging it to solve for specific heat. We have the mass of cobalt, which was given to us in the problem itself. The temperature change we can figure out using the equilibrium temperature and the initial temperature of cobalt. And then now, thanks to the previous step, we also know what the heat or the Q value of cobalt is, negative 1384.9. So plugging those values into this equation, making sure to include that negative sign for the Q value. Once we do the change in temperature subtraction, we also get a negative value for the delta T, so the negatives end up canceling each other out, and we get a positive 0.420 joules per gram degrees Celsius. And that's good that we got a positive because specific heats should always be positive numbers. Q's, our heat values, can be negative or positive, but specific heat, as well as masses, always will be positive. Now is when we also take into account significant figures. Let's look at another problem using the same steps. So feel free to pause and try to work this one through on your own. So for this one, we have a block of copper, and we are immersing it in ethanol. What we need to solve for, it looks like, is the mass of ethanol. So it gives us the mass of the copper, the initial temperature of the copper, it gives us the initial temp of the ethanol, and then also the final temperature of the ethanol. Now notice it says the final temperature of the ethanol is cooled to 52 degrees Celsius. Now that is specifically saying that that's the temperature of the ethanol, but since this is a heat transfer, that is also going to be the final temperature of the copper as well. They also gave us the specific heats of copper and of ethanol. So those will always be given to you unless it's what they're asking you to solve for. So looking at our knowns and unknowns, we have those all listed here. Our plan is to first determine the heat of the known. So the values we have are for copper. So we'll determine the heat of copper first. We'll relate that to the heat of ethanol by changing the sign. And then last but not least, rearrange the equation to determine the mass of ethanol. So first step, determining the heat of copper. So we want to take the mass of copper multiplied by the specific heat of copper multiplied by the change in temp of copper. So plugging in those values, we have 16.05 grams of copper. Its specific heat is 0.385 joules per grams degrees Celsius. The final temp of the copper is the same as the final temp of the ethanol, so that's where we got this 52 degrees Celsius from. We then subtract the initial temp of the copper, which was 12 degrees. Calculating this out, we get a value of 247.17 joules for the heat. Notice the value is positive. So when we compare that value or relate it to get the heat of ethanol, we simply change the sign. So the copper was positive heat value, so that means ethanol is going to have a negative heat value. So same number, just a negative sign in front. So now that we have the Q value for ethanol, we can rearrange the equation for the heat of ethanol, solving for mass, because mass is what the question is asking us to solve for. When we rearrange that equation, we have the heat value in the numerator, negative 247.17 joules, and then in the denominator, we have the specific heat of ethanol, which is 2.44, multiplied by the change in temp of ethanol. So when we multiply by the change in temp of ethanol, the final temp of ethanol was 52 and its initial temp was 68. This gives us a value of 6.33 grams for the mass of the ethanol. So let's look at heat and phase change. So phase change is a physical property in which we are changing the phase of the substance, so going between solid, liquid, or gas. So we're not changing the chemical makeup of the substance at all, we're just changing the phase that it is in. So there's three different enthalpy processes that can describe these phase changes. So the first one is heat of fusion. So when we're talking about heat of fusion, which is represented by delta H fusion, FUS, that is when we are going between solid and liquid. So if we're starting with a solid and it's melting into a liquid, that process then, as I just said, is called melting. Now if we go in the reverse direction, so we're starting with a liquid and going to a solid phase, that process is called freezing. The next enthalpy process, heat of vaporization, deals with the liquid and gas phases. So when you go between a liquid to a gas, you are vaporizing that liquid into a gaseous form. If you go in the opposite direction, so starting with a gas and then forming a liquid, we call that condensation. So condensing down a gas into a liquid. The last type of enthalpy process, a little less common, is heat of sublimation. So this is dealing just with the solid and gas phase. So we're skipping the liquid phase in the heat of sublimation. So if you start with the solid and you skip the liquid phase going directly to a gas, that's called sublimation. So there are a few compounds that naturally do this. Dry ice is one of them. So dry ice is solid carbon dioxide. And when dry ice is heated up, it skips the liquid phase and goes directly to the gaseous phase, forming carbon dioxide gas. So going from the solid to that gas phase is called sublimation. Now, if we were to do the reverse process, so starting with gaseous CO2 and changing the phase into a solid, that's called deposition. We don't see that one very often, but you do need to know that it does exist. So these change in enthalpies of fusion, vaporization, and sublimation are defined as the energy needed to change the phase of 1 gram or 1 mole of a substance. Now, the important thing to note is during a phase change, there is heat energy involved. Okay, heat energy is going into the system. So think about ice, for instance. If you have ice in a glass, the temperature of that ice or that ice water is going to be 0 degrees Celsius. Now, if you apply heat to it, or say it's a hot day outside, and the ice is going to start melting, right? But as long as there's still ice present in that glass, the temperature of the water is going to stay the same. It's going to stay at 0 degrees because even though there's heat going into the system, that heat is going into the system to change the phase. So it's changing that solid ice cubes into liquid water. So it doesn't affect the temperature, but it is affecting the phase. So we use heating curves to describe what is happening to a substance, not only as the temperature changes, which you can see along the y-axis, but also what's happening to the change in phases. As you can see, we have a solid phase, a liquid phase, and a gas phase labeled on this heat curve. So when there is a temperature change, we are going to see that represented by these slanted lines that we have here. So by slanted lines, I'm talking about the ones that are going at a diagonal. So the one that's here going through solid, and then this next one's going through the liquid, and then this next one's going through a gas. So you can see, since those lines are slanted, it is indicating that the temperature is indeed changing. In this case, the temperature is going up. So when we have a temperature change, if we wanted to calculate that stage of the heating curve, we're going to use the original equation for heat that we've already looked at, the mc delta T equation. Now this equation, we will be given the mass, the specific heat, you will find in a table, and you want to make sure that that specific heat correlates to a particular phase. Because if you look at the specific heat table, for instance with water, they have more than one specific heat for water. One of the specific heats for water is when water is in a liquid form, and it's going to have a different specific heat if water is in a solid form, and an even different specific heat if water is in a gas form. So just make sure to pay attention to what specific heat you're choosing from the table or from the problem itself, because they'll probably give you several different specific heats, and the reason they're different is because the phases are different. Now for the phase change steps, so I'm talking about when there's no change in temperature, so I'm going to highlight those in blue here. So these are where we have the plateaus. So in between the liquid and solid slanted lines, we have this plateau here that I'm circling. So this plateau is indicating that heat is still going into the system, because as you can see on the x-axis, heat is still being increased, but the temperature isn't changing at all. And the reason that the temperature isn't changing is because the heat energy that's going into the system is going into the system to change the phase from a solid to a liquid. So the energy going in is changing the phase, not the temperature. So for these stages, these plateau steps, we use a different kind of equation since the temperature doesn't change. So for those ones, we're going to use this Q phase equation. In this Q phase equation, we take N times the delta H. Now this delta H is what we saw on the previous slide. That's the change in enthalpy for fusion, vaporization, or sublimation. And those values will be given to you when you need to use them. Now what does the N stand for? So the N stands for either the mass or the moles of a substance. And we'll do some examples so you can see how that's going to look based off of whether it's mass or moles. It's important to note as well, when the process is reversed, you also need to change the sign or reverse the sign of that delta H. For instance, if they give you the change in enthalpy of fusion, so this is when we are taking a solid and melting it into a liquid, but you need the delta H of the reverse process, so it's freezing instead of melting, make sure to put a negative sign in front of that value. Same thing would go if we're talking about the change in enthalpy of vaporization. If the process you're looking at isn't a liquid going to a gas, but the reverse process, a gas being condensed down into a liquid, then you need to make sure to change that sign on that delta H. Let's do a practice problem and apply some of these concepts that we saw on the previous slide. So in this question, it says what would be the total heat absorbed if the temperature for 100 grams of benzene was raised from 25 degrees Celsius to 115 degrees Celsius. It gives us the boiling point of benzene. It gives us the change in enthalpy of vaporization of benzene. So that means this would be going from a liquid to a gas phase, since it's vaporization. We have the specific heat of benzene when it's a liquid. That's what that little L means after it. And they also gave us the specific heat of benzene when it's a gas. So we want to make sure to use the correct one in the correct spot. Notice we also are given the molecular weight of benzene, which probably tells you that you're going to be converting that gram amount, that 100 grams, into moles. So listing out all the pieces of information given to us, basically writing our list of knowns, we then need to develop a plan. So the first part of the plan is to draw a diagram, much like the one on the previous slide. This is going to help greatly in determining how many steps you need to do, because these are multi-step problems. So some of the problems will have 2 steps, some will have 3, some will have 4. So the diagram will help you figure out how many that you need. Next, once you have the diagram drawn, determine the heat of the temperature changes. So anytime you see on the diagram that you drew a diagonal line, that means the temperature was changing. And then step 3, determine the heat of phase changes. So anytime there's plateaus on your drawing where the heat energy going into the system is going towards changing that phase and not changing the temperature. And then the last step is to add all of those heats together to determine the total heat. So based off of the values given to us in the question itself, this is approximately what your diagram should look like. So you'll notice that there are going to be 3 different steps. So there's one step here, starting at 25 degrees and going up to 80.1. So this is the step in which the phase is a liquid. So benzene is a liquid in this phase. I know this because they told us that benzene has a boiling point of 80.1 degrees Celsius. So when it's between 25 and 80 degrees Celsius, it's going to remain a liquid. So the temperature is going to change, but the phase isn't going to change at all. Once it gets up to 80.1, now you'll notice we hit a plateau. That's because even though heat is still going into the reaction, the heat that's going into the reaction is not changing the temperature. Instead, it's changing that liquid benzene into a vapor, into gaseous benzene. So this is the heat of vaporization process, the plateau process. So once all of the liquid is vaporized into a gas, then the temperature is going to start to rise once again. So we have our second diagonal line starting at the 80.1 degrees right here. And now this gas phase benzene is going to be heated up even further until it gets to 115 degrees Celsius. So we have 3 different steps. The first step with a temperature change between 25 and 80. The second step is a phase change, so no temperature change. And then the third step is this last diagonal line. So you'll notice off to the right, to figure out the total heat, we're going to have to take the heat of the first step when it was a liquid and the temperature went from 25 to 80.1, add that to the heat of the benzene in a gas phase. So this is the third step that I pointed out with the diagonal line, where we went from 80.1 degrees up to 115, and benzene was a gas in that phase. And then we'll also want to add it to that plateau phase, that middle step, where we are changing from a liquid to a gas, the vaporization stage. So we know we have 3 steps. We've outlined the 3 steps here. Now let's apply. So for the first step, where heat is being absorbed by benzene and it's in the liquid phase, we're going to use Q is equal to mc delta T. We will use the mass of the benzene that they gave us, which is 100 grams. We will then use the specific heat of benzene, making sure to use the specific heat when it's in liquid form, the 1.70. And then last but not least, the change in temperature. So the final temp was 80.1 because that's when it started boiling and it was going to start changing its phase. Initial was 25. So doing this calculation, we get 9,367 joules for that first step. So first step complete, now we need to do the other 2. So the second step, which is that plateau stage, when we are phase changing between a liquid and a gas, since there is no temperature change, we can't use the Q is equal to mc delta T. Instead, what we're going to use is the Q of vaporization, which is equal to moles of benzene times the change in enthalpy of vaporization. So we're going from a liquid to a gas here. So to figure out the moles of benzene, which is this N of benzene, we need to take the mass and convert it to moles. So that's what this step in parentheses here is showing. We take the 100 grams of benzene divided by the molecular weight of benzene, which is 78.114, and that will give us the moles of benzene. So we take that moles of benzene and multiply it by our delta H of vaporization that they gave us in the problem. And that was 33.8, notice the units, kilojoules per mole. Okay, this allows for our moles to cancel out, and the units that are left now are kilojoules. Notice we converted it to joules because our very last step at the very end is to add all of these Q values together. So they all need to be in the same units. Whether you want to change all the units to joules or change all the units to kilojoules doesn't matter unless the problem itself is asking for a specific unit. So second step is done. Now moving on to the third step. So for the third step, we're looking at that last diagonal line where we are in the gas phase, and the gas is being heated up from its boiling point, 80.1, all the way up to 115. So those are our 2 temperature values that we will be putting into this delta T part of the equation. Since there's a temperature change, we're using our MCAT equation, mc delta T. Now we still have 100 grams of the benzene, the mass didn't change, but notice the specific heat value. Now that we're dealing with a gas, we have a different specific heat because benzene's in a gas form instead of a liquid form. So the gas form of specific heat for benzene is 1.05. And then the change in temperature, we take the final 115 minus the initial, which in this case was 80.1. Notice we're only using the temperatures of when the benzene was in the gas phase. Calculating this out, we get 3,665 joules. So now that we have the heat for all 3 steps, our final step is to add those 3 heats together so that we get a total heat for the reaction, which is 56,300 joules. If you wanted to convert this into kilojoules, you would move the decimal point 3 times to the left, and you would get 56.3 kilojoules. And this is not going to write very nicely, so let's try another problem. Feel free to pause and try to complete this one on your own. So we're doing total heat once again, and this time it's total heat lost. if the temperature for 60 grams of water was lowered from 50 degrees Celsius to negative 10 degrees Celsius. So they give us the freezing point of water, the change in enthalpy of fusion of water, and then two specific heats. One where water is in a liquid form and one where water is in a solid form. So just make sure you're using the right one in the right step. We were also given the molecular weight of water, showing us that we're probably going to have to convert that 60 grams of water into moles at some point. So we have all of the information listed. Next is to figure out a plan. First step, drawing the diagram, figure out how many steps you're going to have. Any diagonal lines where the temperature is changing, you're going to use Q is equal to mc delta T to solve. Any steps where there's a plateau indicating a phase change, you're going to use the Q is equal to N delta H equation using the change in enthalpy of fusion. Then the last step is adding all the values together. So let's start this. So based off of the information, here's approximately what your picture should look like. Now notice this time we're starting at a higher temperature, so we're starting higher up on the y-axis and moving downward because we're cooling the water. We're going to freeze the water. We're starting with a liquid and going to a solid. So you can see, according to this diagram, that we're also going to have 3 steps. So our first step is the water is initially starting at 50 degrees Celsius. Now the temperature is being lowered. And the water is going to stay in a liquid form until it reaches this point here, which is 0 degrees. Once it hits 0 degrees, then it's going to start freezing. So our first step is between this 50 and 0, when water is in a liquid form. The second step, where the plateau is, I'm going to highlight it in blue, this is where the phase change is happening. So heat is still going, or being released from the system in this case, not going into the system, but heat is still being released from the system. However, the heat that's being released isn't marked by a temperature change. Instead, we're seeing the phase change from a liquid to a solid. The last step, once the solid is formed and we're at 0 degrees, it looks like the water is cooled down even colder all the way until it gets to negative 10. So we have the first step with liquid water, the second step when the water is freezing, going from a liquid to a solid, and then the third step in which water is in a solid form and there's a temperature change because it's getting colder. So 3 different steps, and at the end we'll add all 3 of those values together. So let's start with the first step, in which we are starting at 50 degrees Celsius and cooling down to 0 degrees. Since there's a temperature change, we're using mc delta T. The mass of water was 60 grams. The specific heat of water when it's a liquid is 4.184, so make sure you're using the correct specific heat, in this case, when it's a liquid. And then the change in temperature of water, the final temp of water is 0, so when it starts freezing, and the initial was 50. So when you subtract those two, it's going to give you an overall negative value for our Q of liquid water. So we get negative 12,552 joules. The second step is the phase changing step, where we go from a liquid to a solid. So for this phase changing step, since there is no temperature change, we're using Q is equal to N delta H. To figure out N being the number of moles of water, we need to take the mass given to us of water, which was 60 grams, and divide it by the molecular weight of water. This allows the grams to cancel, so now we will have moles of water, which is what N represents. Now notice for the delta H portion, So they gave us the delta H of fusion. So delta H of fusion is when we're taking a solid and it's being melted into a liquid. So that positive 6.01 kilojoules per mole that they gave you in the original question was representing when you go from a solid to a liquid. But we're not going from a solid to a liquid, we're going from a liquid to a solid. We're doing the reverse. So since we're doing the reverse, we have to change the sign on that delta H of fusion that they gave us. So that's why we have a negative 6.01 here instead of the positive 6.01, because we're doing the opposite direction that the value was originally meant for. Calculating this out, that will give us negative 20.02 kilojoules, because our moles and moles are canceling, leaving us with just kilojoules. So we convert that to joules for ease of adding at the end. So the tricky part here was changing the sign of that delta H. Last step is that last diagonal line where there's a temperature change. So this is when water is in a solid form. So our initial temperature for the water was 0 degrees. That's why it was a solid. And it's being cooled down to negative 10. So since there's a temperature change, we're using Q is equal to MC delta T. Plugging in our values, we still are using that 60 grams of water. The amount did not change. For the specific heat, nope, we're using the specific heat for solid water, the one that has a S in parentheses by it, so 2.06. Now, for the temperature change, we take the final temp, which is negative 10, and subtract the initial temp, which was 0. So this gives us an overall negative value of 1,236. So now that we have completed all 3 steps, we then add all 3 of those values together to get a total value of negative 33,800 joules.